Okay, what I want to have a little look at today is standing waves. But before we look at standing waves, let's just ask ourselves about waves in general. So here's a sine wave, and here's the usual formula for a wave. Now, y gives you the amplitude as usual, so this would be your y. And the problem is that we actually now have two independent variables, x and t. So you could draw two graphs here. If t was our independent variable, we'd have to do it at a fixed x. That means we would basically be looking at one point in space while time changed. And that would be our graph of it for that one point in space. So we'd still get the wave. Or we could do our wave for x, but that would be at one time for t equals. So this would be for x equals x naught, if you like, and this would be for t equals t naught. So we've actually got two independent variables, and we need those because a wave is changing not just in time but in space. Now we're used to the omega equals 2 pi f, so that one's giving us our frequency of our wave, how many times it happens a second, radians per second times seconds. But we've got a new thing in here called k, and that's k is our wave number. Basically, a wave number is going to give you our size of our wave. I mean, what you've got to ask yourself with any wave is, in terms of, it's got a wavelength, but how many wavelengths fit into a meter? And that's where our little k comes into. So k actually equals 2 pi over wavelength. So if we look at that little formula, we go, okay, what is that telling us? Well, 2 pi radians is saying 2 pi radians, and it's dividing by the length. So k is equal to how many radians per meter. Obviously, if we do 2 pi radians in 2 pi meters, then that would give us a k of 1. So that would be a wavelength, a full wavelength that was 6.28 meters long. Right? If our wavelength is very small, right? So if our wavelength is like in micrometers, that's a very small thing, then we're going to get a lot of radians per meter, right? And if our wavelength is very big, like a radio wave, so that's a much bigger number than 2 pi, then we're not going to get many radians per meter. So this is like radians per meter. So that's wave number. Now, with a standing wave, we've got two waves, same frequency, on one point. So basically, you've all probably seen the standing wave, or maybe that one. We've got, would be the second harmonic. Remember, the formula for this is n times wavelength over 2 equals L. So the first harmonic is half a wavelength equals L, then you've got wavelength equals L, then 3 over 2 wavelengths equals L. So remembering that these are antinodes, nodes, nodes, antinodes, nodes, that sort of thing. But what is it? That's what I wanted to talk a little bit about. This is a standing wave. And a standing wave, basically, we might see that one going up and down, this one going up and down and up and down. The thing to remember about this is that at a certain point in the cycle, there's actually nothing on that string. As this one comes up, this one comes down. There's nothing. It'd be nice to, I'd like a high-speed camera so we could see that. So, anyway, moving on from that, what we've actually got is, with a standing wave, we've got a wave going that way and a wave going that way. And they're both the same frequency, so we could characterize them by this formula here. And what they're doing is they're producing an interference. So they're continuously moving into each other, and even when the two big amplitudes move past each other, one of them will be up here, one of them will be here, and so that node stays a node. So it's an interference process where we have this formula being obeyed. N wavelengths over 2 equals L. So what's the actual formula if we do that addition? If we add those two waves, obviously one will be a sine kx minus omega t. They're going to be the same frequency. The other one's going to be kx plus omega t. That just tells us that it's moving in the opposite direction. And if we do the maths with that, I think you're all used to adding sines together. Two sines give you, what do they give you? Sine plus a sine gives you 2 cos a minus b over 2 times the sine of a plus b over 2. So anyway, we end up with this formula for the standing wave, which is equal to 2a naught sine kx, and then we've got cos omega t. So this is what I thought would be a little interesting thing to look at, since we're looking at the standing waves. We're seeing that the amplitude, this would have been A naught over here, is twice as big at certain points, right? So with the standing wave, this amplitude is twice as big as the original wave. But what it also is telling you is that if we have a look here, we've got certain points on the string. So this is the frequency. Frequency stays the same. But what this is, this front part here, the sine kx, is modulating. Obviously when sine kx equals 1, we're going to get an antinode, right? That's going to give you the biggest amplitude you can get. Only at certain times, obviously when the cos omega t equals 1. So when cos omega t, that's what I meant by how when the standing wave is in operation, there are certain points in time where there's nothing on that line. So let's take it that we're at one of those times when the amplitude is at its maximum. So that would need the appropriate t for that. Now we've got the appropriate t, we're at the amplitude point. We could see that the sine kx must equal 1 to get that maximum amplitude. So that's only going to happen at certain x's. So this formula basically will give you the x's where the antinodes and nodes occur. Obviously the sine kx is going to be a constant, so that can only happen at one place. Same as the nodes, where the sine kx equals 0, no matter what the frequency is doing. So this formula gives us all the standing wave information, and I thought you'd like to see it.